Thank you.
Hello, everyone. I'm happy to introduce Adam Dangur. He's a Python developer coming from Bristol, and he will present a talk about another pair of eyes reviewing code well. Thank you.
Thank you, everyone. Hello, I'm Adam, and I'm going to talk about code review. But why am I talking about code review? Well, the inspiration for this talk is really a bunch of people I used to work with who are mostly contributors to the Twisted project. And I was really lucky. I got to experience the really rigorous approach to review that's also present in Twisted, and I feel that I've become a much better programmer thanks to that. And I've also had some really bad code review experiences, the kind of experiences that make you not want to go into work the next day. And I never ever want to make someone feel like that. But when it's your role to judge someone else's work, it's really easy to upset them if you're not careful. And I guess that some of you have experience with code review, maybe even most, because it's kind of becoming a fundamental part of the software engineering process. But maybe because of that, it's often seen as boring grunt work and not a skill that you can hone and get better at. But at my job, I spend almost a third as much time reviewing code as I do writing it. But when I go to programming forums or Twitter or read blog posts about how to become a better programmer, I see very, very little about how to become a better reviewer. And when a programmer starts out, they're often paired with a mentor to teach them how to code, or given kind of like easy fix bugs that they can get trained on. But we're really expected to jump in at the deep end and know how to review code without ever having been taught. So today I'm going to talk about these points: what code review is, how I review code, some common pitfalls and traps that people fall into when they're reviewing, tools which can help make your life easier, and how code review can make you a better programmer. So what is code review? It's a practice where someone looks over someone else's code and they look for things which can be improved. And we usually do this before merging code because we want to catch bugs as early as possible. Yes, we've got automated tests, but code review can sometimes be the final gatekeeper before code hits the real world. And we also use it to catch non-bug defects, which can harm the project, such as performance issues or maintainability problems or something like that. But code review isn't just about making the one change set that we're reviewing better. It's about making all of the software that we ship better. And it's important to think about how we can use code review to improve ourselves and the contributors that we work with. And I saw a talk last year at the Write the Docs conference by Paul Rowland, who I think is also at Europython, and he was talking about how we should stop trying to be code ninjas and rock stars, all those other kind of things that you see on job posts, and we should start trying to be code nurses and code tree surgeons. And I kind of see the reviewer's role as just like that. It's not as thrilling as the ninja feature author shipping something at midnight, but it's really important to the health of the project. And all of this happens within the context of the project's goals, which usually includes shipping code fast, or at least fast enough. So let's back up and go over quickly how we get to the review stage. And in the last few companies I've worked at, it goes something like this. Eleanor, our programmer, is new to the project. She's brand new, and she's looking to make her first contribution. So she picks a task from the task tracker. I'm using GitHub here, but it could be Jira, Trello, whatever you use. And this one is written by me. The name of the user's latest employer needs to be shown in our app's new prototype feature, User Profiles. So she creates a branch so that she can make changes to the code without worrying about breaking it. And using branches for development is a great way to create a low-risk environment for people to experiment in. And it lets a reviewer easily look at the proposed change, just the difference between what's been written and what's currently there. And so Eleanor starts searching around the code, and she finds that there's already a method to get date-sorted employment history. Great. And there's already a function that you can see here that returns a dictionary for a user's profile that's later handled by a view layer and shown in the app. So she adds some new code that she thinks might work. You can see these new 2 lines. And it takes the date-sorted employment history, and it displays the first item of that list in a new field called latest employer. And then she runs the application locally, and she checks her own profile, and it shows her latest employer, Bilbao Inc. So we know that this works. Eleanor has seen that it works. Do we need to spend time reviewing it? Well, in my opinion, all code that's written as part of a team should be reviewed. I've heard objections to this, particularly when the change set is trivial or if it's absolutely urgent. And I'm going to propose that very, very little of what we do is actually trivial. Programming is very hard, at least for me, and authors have an inherent bias towards thinking that their code is good. Even if we waste a few minutes reviewing a change that really is trivial, we save hours later debugging the bug that was shipped when someone thought their code was really simple, but it actually had a typo. And even if we're absolutely certain that the code can't break, a review means that at least 2 people know where this new code is. And if the code is really urgent to ship, and there really isn't someone around to review it, maybe it is worth merging. Maybe you've shipped a data-destroying bug, and you really need to revert it right now. But at the very least, I'd recommend that you do a post-merge review, whatever that is. I won't go into it. So, back to Eleanor. She submits her code for review, and she's nervous because it's the first contribution to the project that she's made. But of course, she doesn't mention that, and she puts the code up for review. So, now we've got to decide who does the review. Who gets permission to merge code is a whole problem that I won't go into, but it's got to be someone with that permission. But at least where I've worked, anyone can do it. Anyone can review code and merge it, and it's just like a trust-based system. And as I mentioned, as programmers, we're biased towards thinking that our code is working, but we're also biased towards thinking that our code is readable. Our comments are readable, our variable names are understandable. So the ideal reviewer is someone who has had no part in writing the code. And if we choose someone who's recently worked on the changed files, then they're likely to have really great context, which will help them find a high number of bugs. And according to a Microsoft study that I read, the most useful review comments, so I guess the most bugs found in most cases, come from people who've actually previously reviewed the modified files. But when we choose people who are recent authors or recent reviewers, that conflicts with our goal to share knowledge with the team. And that might be okay, but it's at least something to consider. But a good workaround for that problem is when you allow developers who are unfamiliar with the code to do a review, but you don't designate them as the gatekeeper. You have someone else have to say, this looks good to me, let's merge it. In fact, when I join a team, I love to jump straight into reviewing as much code as possible. And when there's no pressure of knowing that I have to take responsibility, I'm not the one saying it has to look good, someone else will do that, then it's a great way to learn how things are done. It teaches you, let's say, about a project's quality bar and standards and how the process works from writing code all the way through to shipping it. So, say I want to review Eleanor's changes. This is how I'll go about it. I start by reading the spec. Without reading the spec, there's no way that I can know if the code meets all the requirements. Hopefully, the spec's in an issue tracker, and it has descriptions and examples of how the new functionality might be used, or how to reproduce the bug if there's a bug that we're fixing. And then I check the CI, whatever that is, whatever tool you use. And I hope that it's passing, but sometimes we know that CI isn't always passing, so at least I check that there's no new issues. And CI really should be a signal of whether something that was already there is broken, so it's good to check that first. And then next, I look for evidence that the spec's been implemented. And ideally, that means looking at the test changes. If there's a bug to be fixed, I want to see that there's a passing test which would have failed if the bug were present. And if there's a new feature, then I want to see tests that cover the whole spec. And if it seems like the spec is ambiguous, and I've interpreted it differently to the author, then this is a good time to start a discussion about what we want. That could be with the author, or whoever's responsible for shipping the product, maybe the product owner or project manager, whoever it is in your organization. And then I look at the implementation. I think about whether it has functionality that isn't tested, and that's important because even if the code works now, we want it to be safe from regressions. And I kind of think about which missing test cases could convince me of that. And then I think about whether there's any risk that the changes could break existing functionality. Yes, we've got CI, but it's not always perfect, and it's often a good thing to think about. And then I think about, is the new code going to be easy to maintain? And that can range from things like, are the variable names understandable? But also, I have to think about what the structure of the code is. Is it really branchy? Does it have lots of side effects? Is it idempotent? Is new code in the place that I'd expect to find it? And these are all the things that you think about when you're writing the code. So you get a lot of the advantages of pair programming, but it's asynchronous. And then I check that everything user-facing is documented. That might not be relevant in your project, but it is in mine. And I'm also, at the same time, while I'm reviewing the code, I'm looking out for new techniques and patterns and tools that I don't know yet. And it's always really nice to say thanks to the author when you learn something from reading their code. And then I'll write a comment about anything that might be improved. And I'll ask questions and start a discussion about anything that I'm unsure about. And at the end, I'll give a conclusion. And usually, it's one of these options. I say, great, it looks good to me, I'll merge it. Or, please make the requested changes, and then you can merge it. Or, make the requested changes and then resubmit for another review. And then, sometimes in the rare case, I picked up a review that I'm not qualified for, and I ask that someone else looks at it. And I'd say that the first step to getting better at review, and all those previous steps I've mentioned, is to take it seriously, like we often do the rest of our craft. If you learn about software engineering practices from blog posts, then search for blog posts. If you learn from formal studies, then look for formal studies about code review. And importantly, ask for feedback on your reviews, just like you ask for feedback on your code. So, I look at Eleanor's new code, and I immediately spot a problem. The Twitter handle feed just above is title case, but the new field is sentence case. And so I know that the pull request is not up to scratch, and I comment and reassign the issue to Eleanor. So what are her next steps? Well, she sees my comment, and she kicks herself for making such a trivial mistake. Why can't I do anything right, she thinks. Maybe I'm not good enough to be here. And then she searches the code base for latest employer, the name of the new field, and she sees that it's written just like she wrote it everywhere else it comes up in the code. Beginners don't have the confidence to protect themselves from being hurt, from feeling hurt by code review. And some experienced developers don't either. So what we should do as a community, is be wary of imposter syndrome and use code review as a forum to make this industry a nicer place. But you don't want to let bad things be merged just to avoid hurting someone's feelings. One tip is to always say one nice thing about the code. And when someone's made an effort, there's always something nice you can say. And it's good to always address the patch and not the person. At a previous company, I was lucky enough to be thrown in at the deep end of a project, and that project had quite a steep learning curve. But it took me some time to get into the mindset that my code was being reviewed and not me personally. But what else could be better with this review? Well, Eleanor doesn't know what to do next, if you remember that she was searching around the code base. And one of our goals, the project's goals, is to ship code quickly. So by not making it clear exactly what she's got to do next, I've slowed down the process and I've added unnecessary work for her. And also, you might spot that there's a bug a few characters later. Basically, if that list is empty, get employers, then I'm going to get an index error when I try to access the first item. But I stopped my review when I saw the first problem. And that means there's got to be a whole extra round of review which delays us shipping the code. And of course, sometimes there's a trade-off when you're thinking about when to stop. If a patch is really large and based on a completely wrong assumption, then scrutinizing every line probably isn't worthwhile. So, after a back and forth and a comment about the index error and so on, Eleanor resubmits this code. And I'd say that's a code review success. We stopped a bug getting into production. It's great. And so I start my next round of review, and I comment that a try except clause has performance overhead that we don't want. And the message line is greater than 80 characters, and that violates PEP 8. And finally, I mention that using a getter for the list of employers, to remember that function she found and used, isn't very nice, and she should use a property instead. And on the surface, these might seem like reasonable comments, but it really is not a great review. Because as a reviewer, I need to consider the context, and I need to consider what's important right now. Sometimes it's security, sometimes it's maintainability, sometimes it's speed, who knows. And this right here is prototype code if we remember the spec. So there's no need for me to be overly concerned with tiny, tiny performance issues. So I've kind of wasted some time with that suggestion. And as for PEP 8, well, it's a guide. It's not a rule set. And if you want to follow a guide, fine. But if you want rules, then I totally recommend using a tool or set of tools to enforce them. And that's partly because humans are very bad linters. We miss things that tools catch. And it's partly because if we use tools, then we can free ourselves up to do more important things. And Flake8's one of my favorite tools. It combines a lot of tools, and it enforces the Flake8 guidelines, some of them as rules. And then there's coverage.py, it checks your line coverage, and requires.io, which checks for vulnerabilities and dependencies, and landscape.io, which looks for common code smells and mistakes that people often make. And there are even tests for docs. If you're using restricted text, there's doc8, which lints your documentation, and there's Sphinx's link checker and spell checker, and there are probably similar checkers for Markdown and ASCII doc and whatever tool chain you use. But sometimes these tools will suggest changes that are actually worse. My personal preference is just to always just follow the tool suggestions, and overall your code is probably going to be nicer, and you save the cognitive burden of linting by eye. But if you really want, most of these tools allow you to ignore a particular issue. Like here I've told Pylint, don't worry that the function name is too long. And if a suggestion keeps coming up in your project and your team don't like it, you can just disable some of the checks in most of the tools, or change them. And if you use GitHub, then you can integrate these tools with pull requests, so you can actually make it so that code can't be merged if the tools find problems. And finally, Reviewable is a really powerful tool which has great features that GitHub doesn't have. Like, say you're doing a review, you can say, I just want to see the changes since I last did a review. So if we go back to my review, we see a suggestion of an unrelated change, changing an existing getter to a property. Now, if you want an unrelated change, it's probably best to just make an issue in your issue tracker and deal with it later. A review might be a great place to spot required unrelated changes, but not to request them. Because asking for unrelated changes slows down shipping the code, and it also makes the next review round less pleasant. In fact, as a reviewer, I should request easily reviewable changes. But what are reviewable changes? Well, statistically, more defects are found when change sets are shorter. And as a reviewer, you can ask that a patch is split up if it's difficult to review. And you might be able to help decide where the splits should be. So say someone refactors some code before adding to it, you might ask that the refactoring is in its own separate pull request. And when you spend a lot of time reviewing code, you start to get a good idea of what's going to be easy to review, and you'll start to write code like that. And writing easy to review code means reviewers can be more effective and find more bugs, so your software is better. And when we focus on making a reviewer's life easier, we write code that can be extended without changing what's there too much, otherwise known as maintainable code. And a trivial example of this is the Silicon Valley comma. If I add a comma at the end of that line, then when I add a new item, I only have to see, when I add a comma at the end of Basilica, when I add a new item, I get to see just one new item's changed. Great. And the same for docs, but I'll skip it because we're running low on time. And I'm going to say that the best reviews aren't just laser focused on providing the bare minimum needed to ship, but they also don't add unnecessary blockers to merging. And when you explicitly state that a suggested improvement is optional, and you can let the author choose whether, let's say, to learn a suggested tool or to just skip it and ship now, then that can be really useful. And those priorities can be adjusted depending on the context. And let's say if you've got a brand new developer to the project, you're onboarding someone, well, you can be super picky and get them in sync with the rest of the team, or you can be easy because you want them to feel happy and get started quickly. And so every review comes with a mini, how would I have done this? When we read someone else's approach to the answer to that question, and we notice that their approach is better, or at least better in some way, then we learn techniques and patterns from them. And I find that teams which value review get really much better reviews back, and they get reviews done more quickly. And my favorite example of this is Twisted's high scoreboard. So you get a score every month, and you get some points for submitting, but you actually get the most points for doing a review. Thank you very much for having me. I haven't put them up yet, but I'll put my slides up there, and I'll probably tweet about it or something. Hopefully you can find the link later. So are there any questions from the room?
We have a few minutes for questions.
I have just a quick one. What's that score thing that you showed in the end?
That's Twisted. So Twisted is an open source project. It's like a networking framework, and they want to encourage people to contribute. So just as a bit of fun, they've got a high scoreboard, and so who's been the best contributor this month, or the most prolific contributor this month? So you get like 100 points or something if you, let me go back to it. Oh, where were we? Yeah, if you're 200 points if you submit some code, and 500 points if you close a ticket, but you actually get 1,000 points if you do a review, because they have a backlog of code that's been submitted and not reviewed. And so there's no point having new code if the code that's already been submitted isn't merged.
Hi, great talk.
Thank you.
So when you review your code, do you also suggest to check out it and test it, like if
Yes,
it's more complex?
I took that out
or
because
is
I
that
was-
not part of your job as a reviewer? How do you stand on this?
So I don't always do it. Sometimes the tests hopefully tell me enough. If there are no tests, sometimes there's a good reason that code isn't tested. Let's say it's prototype code, we're going to throw it away, or maybe it interacts with an external service and it would just be really costly to build a fake for that service. What I like to have is a reproducible manual test case. So let's say if it's Elasticsearch, connect to Elasticsearch, check this in the web interface after you run my code or whatever. And I like to get my editor out, I like to get my web browser out, run it, and check that works. And also, if I've got a suggestion and I'm not like 100% sure about it, I like to modify the code, see if my suggestion might work, at least in a prototype stage, or see if I can break the tests by modifying the implementation, or make the test still pass by modifying the implementation in a way that the functionality would break, and then I've found a flaw in the tests. So I do get my editor out.
Thanks for the great talk. I have a question regarding the size of reviews, how to handle it, because if you have a feature that needs to be implemented, but the change that would be too large, how do you handle a case like that? Do you make earlier pull requests with only a partial implementation of the feature, or what would you suggest?
So I like to always keep master or trunk or whatever you call your main branch working. And so one way that people do it is you make a branch for the whole feature, and then that's just empty, it's like master, and then you make branches off that, which have all the partial features, and you put those branches into that first branch I mentioned. I should have given them names, and then eventually when you're happy with it all, you've got this huge diff, and you merge that into master.
Hi, Megan. What about the time spent? What do you suggest? Like, you can go really in deep, like reviewing every line, texting or every line on
Cool. So it depends on a few things. One, I never want to be tired in a review. As soon as I'm tired, maybe like 45 minutes in, my review is useless. I'm going to miss bugs and stuff. But as for scrutiny, how it really depends on the context again. If I'm reviewing something right at the core of my project, it needs to be great. I'll spend as much time as needed. Or if it's, let's say, an API that's going to be really tough to change later because users are going to depend on it, then I'll also be really deep. If it's something in the middle, or like I mentioned before, prototype code or something like that, then I can say more like trust, or, okay, I've opened this up in a web browser and it all seems to work, so fine, or at least something a bit closer to that. And like I said at the end, if it's a beginner programmer on your team, then maybe you want to be really picky just to help them along, or something like that. It depends on the person as well.
Last question.
Oh, sorry. So imagine you have like several issues, and all those issues can be resolved in maybe 1 or 2 lines of code. Do you favor like several commits or just one commit?
So different projects do it in different ways. Some people like to review the commits. It's quite nice when you've got a set of commits to be able to just revert one, or to see a history. Why did that come up? That's the advantage of review of commits. But usually in my reviews, at least where I work now, I don't deal with commits. So that's a different practice that lots of people do, but I don't. So I'm sorry, I don't have a great answer for that.
So we are running out of time. Thank you very much for your
Thank you.
insights.
Thank you all.
place, but you can take that maybe. So, welcome everybody. I'm happy to introduce James Sayawini. He's a software engineer working at Amazon Web Services, and he will present a talk with the title, Writing Redis in Python with Async.io. Give him a hand, please.
Hi, everyone. Welcome. Thanks for being here today. So as mentioned, my name is James Sayawini, and today I'm going to be talking about writing Redis in Python with Async.io. A little bit of background. The reason I started this project in the first place was really I just wanted to learn more about Async.io. I had heard a lot about it. Everyone was talking about it. I've read the docs, but I didn't really understand how we could use this to write something a little more realistic. And at the time, I was familiar with Redis, and I thought, Redis has some features that looks like it would be a really good fit for Async.io. So I wanted to see how far I could take the idea. So I started exploring writing Redis in Python with Async.io. And the reason I want to share this today is because I think there's some useful things that everyone here can take away from it. I want to show how you can structure a larger network server application. That wasn't very obvious to me from reading the Async.io documentation. And then I want to show you a couple of patterns that happen in Redis that I think apply in general to various types of network servers. So the basic request response structure, how that looks like, and then also a couple of other ones that are interesting. So publish, subscribe, and then blocking queues. So if you're familiar with Redis, this would be the BL pop and the BR pop, the blocking left pop and blocking right pop. By the way, if you're not familiar with Redis, that's okay. I'm going to be explaining all of the specific features we're going to be implementing, so don't worry about that. But I think that these patterns apply to, say, a chat server or into any kind of your own task queue or job queue. And I think in general, these would be generally applicable. Before we get started, though, before we dive into it, I just want to give a little bit of a disclaimer. I'm not an Async.io expert. As I mentioned, I wanted to learn more about it. So a little bit about me. I work at AWS, and so I primarily work on these are the libraries I primarily work on or have written a substantial portion of. And the point of this, though, is that my area of expertise is in Python libraries and supporting multiple Python versions, that kind of thing. So writing an Async.io network server that only runs on the latest version of Python is not something that I would consider myself an expert in. So I'm just a beginner trying to share what I have learned. So without warning, as much as I'm going to try to shoot for this, which is probably what the experts and the Async.io maintainers would want us to do, there's just a chance we might end up, with something like this or something crazy like this. So just as a warning. Okay, so the 1-minute introduction to Redis. It is a data structure server, so it's a network server. You run it on a machine, you connect to it via sockets, and you send requests. It gives you responses. The one thing that's kind of interesting is values can be more than strings. So you have your basic case here where you can set, foo and bar, and you get a value back. And then I can also get a value, and it'll give me that value back. But in addition to that, I can also have lists. So in this case, I can say rpush, which is a write push onto the foo list, the value of a. So this is like foo.append a in Python. And I can do that for 3 elements, a, b, and c. And then on the right-hand side, I can say lpop, which is left pop from foo. That's going to return me the first element, a. And then I can do lrange from foo 0 to 2, which is basically a slice. So that's going to give me the elements from 0 to 2, which in this case is b and c because we popped a previously. So that's the first thing I want to shoot for. And I'm going to look at how we can do a basic request response. So at the end of this first section, I want to be able to send a GET request, interpret it, figure out how this is going to work, and then send a response back. So I think, what most people would do, start at the documentation. If you haven't seen the documentation, this is the Async.io docs. You start at section 18.5.4.3.2, the obvious place to start, which is the TCP echo server protocol. And so I changed one line here, but this is essentially straight from the docs. And by the way, I'm going to be showing a lot of code here. I'm going to highlight the specific parts that I think are interesting, but it's okay if you don't have to follow or understand all of this. I'll put the slides online so you can look at it more in detail later. But there's 3 parts to setting all this up. The first thing we're going to do is create an event loop. We're going to then call create server and give us the Redis server protocol. So this is the class we're going to write, and this is going to give you all of the logic for handling the Redis protocol, parsing, figuring out how to call into our database, all that kind of stuff. And then this will set up the listening sockets. The next thing we're going to do is call run forever. This will wait for network I/O and then call the appropriate things into our protocol. And we'll look at that in a second. And then the last thing we're going to do is just clean up. So once we want to exit, we close down the server and call loop.close. But I want to look at this Redis server protocol. I should mention real briefly that there's, I think, 2 other ways you can do this. You can use the low-level sockets in the async I/O loop, and you can also use streams. Streams are a little bit higher level. What I found is streams, while they were really nice to use, the performance for me was it was substantially slower, and I think protocols for me was a nice middle ground between still being fairly expressive, but having pretty good performance. I'll show some performance numbers at the end. So here's a protocol. So the idea is you have connection made, data received. You get a transport for connection made, and then when data is available, you call data received. So I looked at this, and I kind of understood what it was doing. I think that there's some history there from some of the other frameworks that influenced this, but I still didn't really get how protocols worked. And for me, going one level deeper into async I/O and trying to understand how all this works really helped illustrate for me. So I'm going to go kind of briefly into async I/O code to understand how protocol and transports work, because that's really going to drive a lot of this implementation. So first thing, start with the Redis server protocol. And in this loop, what's going to happen is whenever a connection's made, async I/O, notice in the top right, this is async I/O/selector events. So what's going to happen is you have a callback. Whenever a connection's made, you call accept connection 2. And what's going to happen here is, notice a protocol and transport are created for every connection. So every time you have a client connection, it's going to create a protocol and a transport. And this part here with the protocol factory, that was the Redis server protocol class we passed in. And notice it was a class object, not an instance. So it's going to call our class that's going to return an instance. But the main thing here is that there's one protocol and transport per connection. So if I had 3 clients connected, I would have 3 transport protocol pairs. And the next thing now is, let's see how connection made and data received are going to be called. So if I look at, this is the selector socket transport, still in the async I/O code. When you create it, there's this first line here, which is self.protocol.connectionMade. ConnectionMade is this thing that we're going to write, and we can see how it's going to be called. The loop.callSoon, I found that kind of confusing. It's really just loop.schedule this thing to be run, or loop.add this to your to-do list of callbacks. But essentially what this is asking is for this method to be called, and then the arguments to pass. So notice that the last argument is self, and the class we're in is a selector transport. So we'll see that again when we go back to our protocol class. The next thing here is the read ready method. So again, another callback, and look at the last argument, it's read ready. And we'll dive into what read ready is, still in the async code. Again, just kind of showing you some highlights here. And the main part of this is this protocol.data received. Again, this is the method that we're going to write. So what's happening here is whenever there's data on a socket, we'll read from it via socket.receive, and then call data received. So the main thing here is that these are just callbacks. So they're not coroutines, they're not anything, anything fancy like that. We just saw, they're just simple callbacks that get scheduled whenever a new connection is made. And so if an event loop was like this, going from left to right, if I had 4 connections, as data comes in, I'm going to call data receive onto those protocols. So hopefully that gives you an idea of how protocols and transports work. So we can start fleshing out the basic get and set response here. This is how a more realistic data receive might look. So the first thing we're going to do is we're going to get data over the wire. We're going to call into our parser to parse the wire protocol. I'm simplifying things a bit, and I'll discuss that at the end. But we're going to parse the wire protocol. And so this will give us, say, a list where the first element is the command set, next one is a key, the next one is a value. And then once we do that, we're going to look at what command we were provided. And then after that, we'll call into the DB layers. So we'll say self.db.get and self.db.set, and we'll look at how that looks like. And then finally, after that, we're going to take our response, ask our serializer to serialize it to bytes, and then use transport.write. So a transport is really just an abstraction over a socket. It allows you to write data back to the client. So whenever we have something to send to our client, we say self.transport.write. And so this is the basic overview for the first part. And also notice in connection made, I should mention, we're storing the transport. So that's how we're able to write back to that client. So it's one connection. And then just to give you some concrete data, this is, you don't have to know what this is. This is the Redis serialization protocol. So it's a text-based format. This is just how it would actually look like. We'd get data over the wire that looks like this. Star is like the list type, and it's 3 elements. And you can kind of see there's a set foo bar there. And then this is what we would return. So just to give you an idea of what we're actually sending back over the wire. Okay, next thing, the DB class. So this is where all the logic happens for the Redis commands like get and set and all the list manipulation. As you can see here, it's just essentially an abstraction over a dictionary. But the main things here that I found the DB being a separate module, so it doesn't know anything about async IO. That's really helpful. So you can imagine how you'd write a unit test for this, right? You create a DB, you call set foobar, and then assert, db.get is going to equal bar. So very straightforward to test. Here's how some of the list commands would work. Again, just hopefully you can kind of just get the gist of this, right? For our push, we're essentially going to manipulate a list. For the L range we looked at, it's looking up that key and then slicing based on the start and stop. And same thing with lpop, or popping from the front of the list. By the way, use collections.dex so you get the constant time pop left. But just as an example, we're going to use a list here. And you can see how you can start to integrate that into the protocols here. So, realistically, you'd probably extract this into a command handler class. But here I'm just adding if-else statements here that are going to say, if it's our push, we're going to figure out how to construct the appropriate call into the database layer. And we keep that nice level, that nice separation between the async code and our logic. Okay, so at this point, we've covered the basic stuff. We know how to get, we know how to respond to a get and a set and a list command. You could use this to flesh out the other types. So sorted sets, hashes, all that kind of thing. You can get a lot of the commands implemented this way. But now I want to cover two more interesting cases that I think took me a while to figure out. So the first one is publish subscribe. What we want to go after here is we're going top down. So we have a client that connects and says they want to subscribe to a channel called foo. And then we have another client that wants to subscribe. And what's going to happen is at some later point, if another client comes along and says, I'm going to publish on the foo channel this message, we want to be able to write to every subscribed client for that channel that message. And then just to give you something a little more concrete here, it's that same example that's actually using real Redis and real Redis CLI. So what you'll see here is I'm going to subscribe to 2 channels. And then on the 3rd channel here, I'm going to publish. And the main thing I want you to see is when we publish in the bottom thing here, you should see the top 2 get the message. And that's what we're shooting for. So we're going to publish 2 messages. Here's the first one. You can see how both got that message, and then we do it again. And so then they both get the next message. So that's ideally what we're trying to implement here. So how do we do this? If we remember that we had one transport and protocol per connection, we need something a little bit different. We need to be able to, from a given transport protocol pair, somehow communicate to other transports that are interested and write data to them. And what we're going to take advantage of is this protocol factory. So I showed you some async IO code where we were doing protocol factory and instantiating it. We're going to take advantage of that in a second. But the actual pub/sub part is pretty easy. We're going to create a new class, and whenever you call subscribe, we just have a dictionary of the channel name and a list of transports. So you give it your transport when you want to subscribe to something. And then the publish is equally straightforward. You look up the channel, you have a list of transports, and you iterate for every transport in transports. You just call transport.write. And hopefully that's pretty straightforward. There's not really a lot of async code there. It's actually pretty simple. And the way we integrate this, same thing, we're going back to our Redis server protocol. So in this command here, we're just calling our pub/sub object .describe, and notice we're passing our self.transport, and then same thing with publish. So this part's pretty straightforward. The thing that was kind of tricky is how do we actually get all of this stuff wired up together? And so you remember this very first line we looked at, which is we're passing a class object here, not the instance. We're going to change that slightly into a protocol factory. And now we're going to pass the factory to the create server. And all this is going to do is just store a reference to the class, and it's going to store args and keyword args to pass. So this is also basically like functools.partial, if you're familiar with that. This is just kind of making this a direct concept in the code. So now, whenever this gets called, we're able to pass in a shared object. And so the thing that was useful for me here is that instead of having transport know about other transports and having to coordinate all that, you just tell the pub/sub object, and the pub/sub manages which ones it needs to call out to. And so that, again, keeps your logic very simple, very easy to test. So that's publish subscribe. The last thing I want to look at, that's probably the most interesting one, is blocking list pops. So this is what we're shooting for. I'm going to subscribe to BL pop, which is a blocking left pop. On the foo key, and 0 is just a timeout, which means wait forever. So if I do that with 2 clients, notice I don't get a response right away. But now if another client comes along and does an R push on the foo list, I'm going to pick that value, the bar value, and send it to whatever client's been waiting the longest. So this is essentially like a queuing system, right? And again, just to give you something more concrete, we're going to do the same thing here. Create 2 clients. We're going to have both of them block. And we're going to publish 2 messages, and this time you'll see one client gets the first message, and another client gets the second message. So hopefully you get what we're shooting for. We only want to give it to one. So now we need to manage which one's been waiting the longest. So how do we do this? This one was also took me a little bit of time to figure out. Wasn't intuitive to me, but we're going to use the same idea, where we're going to use a shared object. So this is a key blocker object. And the way we do this, we'll start at the bottom and kind of work our way up. So remember that database object, which is not supposed to know anything about async IO. So what I did here was the same idea where, if there's something in the list we don't have to block, we return right away. But if there's something that we do have in the list, or if there's nothing in the list, then what we need to do is block. And instead of having the database object know how to block and start integrating and coupling async IO code, it just returns some sentinel value that says, you have to wait, right? I don't have any data available. Whoever's calling me needs to figure out how to wait. And if we go up one level of the stack, we can see in our data received, same kind of thing here. We're going to pass in our database and our key blocker and our loop. But here we're going to call it BLPOP, same stuff as before. But if we get something that indicates we need to wait, this is kind of the new part where we're going to look at async and await here. So I'm going to call key blocker, this new object, .wait for key. I'm going to get this thing back. Really, it's a coroutine. And then we're going to say loop.create task, this coroutine. So remember earlier I showed you how the data received was a callback. And one of the important things there is that you cannot block that. If you block that method, you block the entire event loop, right? And everything stops. So the best that we can do if we want to block for something is create a new task. So if you're familiar with threads or something, create a new thread conceptually and ask the event loop to run it. And that thing can block. So that's essentially what we're doing here. We're creating a new coroutine, and we're asking the event loop to run that in its loop. Okay. And then now that we have the corresponding blocking part, we need the push part. So whenever data comes into their push, we're going to tell the key blocker about it. And that's this part here, where we're going to say, create a new task with data for key. And so now let's look at how the key blocker looks like. And so there's a couple of new things here. There's the new async and the new await stuff. And we'll go over how this works. So the first part is the async def, wait for key. This is new to Python 3.5. This is creating a native coroutine. And the important part here is that we're going to use an async io.queue. So if you're familiar with the queue.queue that's used for multi-threaded, in a multi-threaded scenario, it's kind of the same idea. And essentially what we're going to do is block. So we're going to say value equals await queue.get. And what this is going to do in this coroutine is it's going to sit here and wait until there's actually data available. And because we're using the async queue, which gives us the FIFO semantics, it will unblock the one who's been waiting the longest, right? First in, first out. And so once we get our value, we can then do the transport.write for that single, only that single transport. And then we have a corresponding thing for data for key. We don't technically need to use it. There's a queue.put no wait, but I just wanted to show how you could also do that. Okay, and I found async and await, while conceptually it's kind of easy. You just put like await where you would want to block normally. I wanted to know kind of how that worked. So here's a very, very high level overview of how async and await work. So what's going to happen is we did the call soon, right, for our task. So we have wait for key happening in the event loop. So the event loop comes along and says, all right, we're going to call this method. And then remember, we called queue.get. And one of the things that I realized, was that whenever there is an await, somewhere deep buried in the guts of async IO, there is a yield somewhere. That is the only way to stop Python code from executing and essentially save the state so you can resume it with a coroutine.send, right? So there is a yield somewhere deep in async IO. And at this point, we go all the way back up thanks to the magic of yield from, and we have this object future. Doesn't really matter. This is kind of like what it's called. But what happens at this point is this is essentially frozen. So the event loop knows about this call stack and it's frozen. And then something else comes along when data actually is available for the key. And we say data for key, which is going to do the queue.put. And that queue.put is then going to have a value associated with it. And again, I'm kind of glossing over the details here to simplify things, but what's essentially going to happen is this is going to unlock the future. So this is going to say that this future is done, which will then schedule it to be run in the event loop. Then this value here goes over to the yield and resumes, and then now you get that value back from your queue.get. So at a very high level, you can kind of see how that would work with this async and await here. That's essentially what's happening here. Okay. So that is basically how you would do blocking list pops. You do the same thing for BL pop and BR pop from the end of the list. There are a few additional considerations. There are things that I didn't really have time to cover that actually change a lot of how the internals work. So first thing, the real parsing is more complicated. So I made a big assumption that we're getting all of the data as a single request. Realistically, you would get partial data, you would feed the parser, and it would tell you when it had a complete command for you to run, and you could potentially get more than one command if you're doing pipelining or that kind of thing. PubSub can handle clients disconnecting, right? So there's also another method on the protocols that we didn't look at, connection lost, and that's how you can handle disconnecting. And there's also like some advanced pattern matching, that kind of stuff. And then the last thing is that blocking queues can actually wait for multiple queues. So I can say blpop, foo and bar, and then when data is available on either of those, it will unblock. And so for that, I couldn't use an async io.queue. We actually had to go a little more low level and use the async io.futures. Okay, last thing, performance. I was curious. So there's a Redis benchmark program you can run that comes with Redis. These are the parameters I did, so just the basic set and get. And on my laptop, Redis server, we got about 82,000 requests per second. For Pi Redis server, I got 24,000 initially. I was at Yuri's talk with, he was talking about UV loop, so I thought, let's try it out, see how well it does. And just plugging UV loop with no changes brought it up to 38,000 requests per second, so I thought that was really cool. We're a little more than 2 times as slow. Very unoptimized code. When I profiled it, it was mostly in my parsing code, which can be optimized quite a bit. It's inefficient how I'm doing parsing now, but I thought that was really cool. So we're pretty close. So just a summary of what I covered here so far. Looked at transports and protocols, hopefully showed you a little bit more in depth how they work, how they pair to a single connection. And then we looked at request response and then some other patterns for how we can share state or how we can communicate state across various transports. So looking for publish, subscribe, and then blocking queue-like behavior. So I'm going to put these slides online. I don't know where they are, where they're going to be yet, and I'll put the code online as well. I don't have links, so I guess for now I'll tweet them out eventually. So that's probably the best place for more information. But once again, thank you.
Thank you very much, James, for this talk. We take a few questions.
Hi, great talk. Why did you write your own path instead of using a pre-existing parser? There's, for example, the high Redis parser. That's a C interface to the C parser of Redis.
Yep. Good question. Mostly just to see what the overhead would be, just kind of learn more about. I mean, mostly this was a project to learn more about how Redis would work and how to implement it. But I think if I was actually going for performance, that would be the next step is either try to clean up the parser myself or to just use the high Redis, which is a C library, to do the parsing for me. And I think that would get pretty close performance to the real Redis. So yeah, that's something I want to look into.
Okay, some more questions on the back.
Hi, great talk. You made the tests with RADs with persistence or not?
Oh, are you asking about if we persist the data to disk? Like
yes, yes.
So that's not something I'd looked at. I don't actually know the best way to do that. So with Redis, it just does the fork and exec and then writes it in the background. That would be my first attempt. It would to do something similar. Try just the fork exec and figure out the serialization, the RDB serialization, and see how well that works with async IO. But I haven't actually tried it.
Okay, thanks.
Okay, one last question. There it is.
And what do you think about async IO? Did you like it, the experience? Or what's your conclusion of?
So I think one of the biggest problems for me was just it was hard to figure out how to do things. And I think, not coming from a background of writing a lot of async IO code, I think the docs, and I think I heard this mentioned earlier, the docs need a little bit of work. It was not, I could understand how building blocks worked and how coroutines worked and tasks and all that, but I didn't really get how to fit things together. And I think just having more examples, having more documentation about that would really help. As far as the internals, I found it a little confusing. For the people familiar with async IO, how you have futures and tasks, which really should be called like coroutine driver, and how that schedules things, and you get futures that then have callbacks, and the way that kind of works, I found that a little bit hard to understand. I've been looking at some of the other ones, I think, frameworks like Curio was one that seemed a lot simpler for me to understand. But I think for me the biggest problem is just having more examples of how to do things, and then it's a great framework.
So yeah, thank you very much for your talk again. Give him a hand.
you want to test it? That sounds good.
Yes.
1, 2, 3.
El commands.
Let's slow her down. Okay.
Down.
Perfect. How's that? There you got a free preview of the whole slide deck there, everybody. At least I know it looks okay.
Hello, our next presenter is Joe Drumcool. He's head of developer advocacy in MongoDB, and his talk, a deep dive into the PyMongo MongoDB driver, is going to start now. Thank you.
Thank you. So a quick poll so I can know how many slides I can skip here. Who here is new to PyMongo or MongoDB? Okay, we'll do a little bit. Those experts amongst us who've crashed through replica sets and sharding will just bear with me for a couple of minutes. My name is John Will. As I said, I run the developer advocacy organization for MongoDB in Europe. So my job is to get you to start using MongoDB and to stick at it, right? You know, those other databases, they're no good. MongoDB is going to rule the world. We've been doing this for about 9 years. It's a pretty mature database, and it's designed from its onset to take away the pain of programming. Anybody who's ever built a program with an SQL database knows about the pain of object relational mapping and the horror of taking beautifully written object-oriented or functional code and casting it into SQL statements. So from its onset, MongoDB was designed with a set of native drivers in mind. Drivers are essentially the client APIs that allow you to interact with the database. And it was purpose-built so that you wouldn't even have to know about JavaScript object notation pretty much, which is the coin of the realm for the database. That's what we store in MongoDB. It's JavaScript documents, not Word documents and PDFs, but JavaScript object notation documents. But when you interact with a driver, like the PyMongo driver or the Java driver or the Node.js driver, you're using the types and the objects of the language that you program in. So in Python, you're using dicts and tuples and arrays and date times and all the objects you know and love. So although underneath the wire, we're all JavaScript and actually a binary version called Bison, which I'll talk about, you don't need to worry about any of that. We handle all of that complexity for you. And then beneath that, then again, we've got the document model, which is JSON-based. And then underneath that, you can effectively go straight to one of the storage engines. So the default operating mode for somebody downloading MongoDB for the first time is they run up a single node on their laptop. And in that instance, you're running directly with what we call the Wired Tiger storage engine. It's the default storage engine in version 3.2 of MongoDB, designed to be highly performant and to run very efficiently on clusters with high memory instances with lots of cores, right? So that's the design center. We also have a legacy data engine called mmap, which we used up to version 2.6 of MongoDB. If you're running legacy applications built on 2.6 or versions of MongoDB before, you can start off using mmap before you do the conversion. We also have an in-memory database in beta at the moment. That'll be generally available in 3.4, which comes out at the end of this year. And we have an encrypted database. So if you're storing credit card information or you're doing e-commerce data or you've got medical data or anything that you want to make sure is secured at multiple levels, we can put it in the encrypted storage engine. But the key thing is these layers are essentially insulated from you. They're operational decisions. The driver doesn't care about them. The driver works independently of all of those layers. So the great thing about MongoDB is you can start running a single node, then move to a replica set or a sharded cluster, change storage engines, move to an encrypted storage engine. You don't need to change a single line of code. And that's the real utility of MongoDB. You separate the concerns of operational deployment from development. And we have a range of security and management frameworks and technologies that wrap around this for our production deployment. I'm not going to talk about any of that today. I can direct you to lots of information on that for anybody that's interested at the end of this talk. And we're doing lots more talks about MongoDB at the MongoDB Europe conference on November the 15th in London. I do recommend you sign up for that, and I've got a discount code for that for anybody that's interested as well. And so the drivers support just about any programming language you could conceivably use in the modern world. Obviously Python, we're here today, but PHP, C++, C, .NET, Node, Java, of course, Ruby, and a lot of the frameworks. So we're ubiquitous. And we're no longer in these kind of monocultures where there's just one programming language rules all. A modern, distributed, mature development organization uses the most appropriate language for the most appropriate time and place. So being able to support all of these languages is important. And one of the key tenets of the driver philosophy in MongoDB is that drivers should have effectively the same semantics so that when you move from Java to Python to Ruby, you don't have to radically relearn what you're doing. And so a lot of the semantics we're going to talk about today are essentially cross-driver in their application, although I'm going to talk specifically about PyMongo. Now, underneath the covers, we don't use just standard JSON. If you were putting JSON text into the database, it would be horrendously inefficient. You'd have to reparse it every time. So Bison is essentially a binary encoding of JSON. It's a public spec that's available. And the BSON essentially adds two things that we don't get from JavaScript. Type information, so I can tell ahead of time this is an int or a document or an array or a null or a date time. And length, so I can skip objects efficiently. So I can run down a collection very efficiently. I can tell if there's this many objects of this size, I can skip to the end, I can seek into it. And every driver uses BSON. So every driver will have a BSON library included inside of its driver code. And BSON is usable whether you use MongoDB or not. So lots of people take the BSON capabilities out and just use them as an encoding mechanism for JSON. And in fact, there's a company in Germany that is doing exactly this at the moment. And if you want an example of what they're like, well, they're like Google Protocol buffers or Thrift, or if you're as ancient as I am, Abstract Syntax Notation 1, ASN1. So it's essentially a binary encoding of text data. So there are three standard topologies or layouts of servers that you're going to see in MongoDB. And it's important that you understand these for what follows, because the way in which we interact with these clusters is the way in which we will understand the driver helps us. So the standard one that we start off with when we download a developer kit from MongoDB and we get a driver from APIs.MongoDB is I run the driver, I run some application code which links the driver in, and I connect to a server. I've done this on my laptop a million times, and it just runs a single MongoDB process which points at generally /data. The data files are there, great for development, not recommended for production or anything other than development, but very simple to get up and running. The next and the most common deployment for MongoDB is as a replica set. And a replica set is the way in which we establish durability concerns over the data. So a replica set essentially allows us to say, how important is this data? And therefore, how many copies do I want to keep? And how are they distributed across a particular cluster of systems? So if you look at our MongoDB Atlas service, which is our database in the cloud, we mandate that each replica member is in a separate AWS region. That means we're isolated in terms of network, power supply, and geography, so that we can guarantee that even if a region goes down, a replica set will survive. So replica sets are designed to give us data durability, and they're constructed as a primary, this node at the top here, which is designed to only accept writes. You can't write to any node in a replica set except the primary. And then a set of secondaries. In this case, the canonical replica set is a 3-node replica set, which gives us fault tolerance for any single node failing. But you can have up to 50 nodes in a replica set. And so when we write to the primary's job and the replica set as a whole's job is to ensure that those writes are replicated to the secondaries. And we can specify a concern called a write concern that tells us how important those writes are to us. So if I'm writing log data, I might set the write concern to be just acknowledged, which essentially says I get a round trip to the server and everything's funky-dory. If, on the other hand, I'm writing transaction data for a bank, I need to ensure that every write goes to the server. In this case, I would specify a write concern of majority, and that will ensure that a write is only returned as successful if a majority of the nodes accept the write. And write majority is the way most of our production clusters run. So replica sets fail. And so if the primary fails, now I have a node I can't write to. Well, the replica set's designed to automatically recover from this. And the way it recovers from this is it has an election. So the remaining nodes agree on the most stable, most up-to-date member, and they elect that member as the new primary. So what we get there is that secondary now becomes the primary. We now have a stable replica set again, and now it can accept writes again. And that typically happens in 2 to 3 seconds and can be faster if you've got a faster network and faster clusters. And then recovery is when we add the other node back. It will essentially do a sync with the primary and come back up with a complete copy of the data. We're now back to where we were. Note the primary is moved, and the whole idea is that the primary can rotate around the replica set at will. We don't really need to care where it is because the replica set will manage handling where the primary is. And part of what the driver allows us to do is to establish the connection to the primary when it moves or when it fails. And we'll talk about the protocols that it uses to do that in the next couple of slides. The last cluster environment is the sharded cluster. So the sharp-eyed amongst you will have realized that there's a finite limit to how much traffic you can pump through a single node in any compute cluster. So primaries give you a cap, and it's essentially a cap on the amount of bandwidth or memory or CPU that that single node can handle. Well, a sharded cluster essentially removes that limit by allowing you to run a unified cluster in which there are multiple replica sets which give you multiple primaries. And in that scenario, we run some additional daemons called Mongo S's, which are shard routers. They route queries, writes, and reads, and deletes to the appropriate shard based on a key that you define. We're not going to talk too much more about sharded clusters today, although you should be aware that when we talk about what's happening in the driver, very similar driver code is used in the Mongo S to establish and manage connections between the Mongo S's and the driver code itself. The key thing to remember is your driver doesn't change. Single node, start off. Move to replica set, don't change. Move to a sharded cluster, don't change. There are some code changes we suggest you make, and we're going to talk about those to handle failures that happen at the replica set level. So the driver does a bunch of things. It's not just a kind of a passive API, a library that you load. It's more often than not in libraries like PyMongo in Java, it's a multi-threaded client. So it starts additional threads. So it handles authentication and security. It does the Python to BSON mapping that I talked about. It handles the error handling and recovery for the event that we see failures. It manages the wire protocol, so how we bundle BSON objects onto a socket and send it to the server and handle those responses. It also has a connection pool so that we can essentially manage a set of connections over a set of servers where we don't have as many connections as we have clients. And finally, it does topology management. And that's a very specific choice of words because there's a specification, which I'll show you at the end, which defines what topology is from a driver's perspective. And topology is essentially the driver's understanding of what a cluster looks like. And so a lot of what we'll talk about for the rest of this talk is how the driver gathers topology, understands it, uses it to allow the client to interact, and recovers when the topology changes. So if you look inside the PyMongo code, there is a topology object that encapsulates all of this interactivity. And so when you start reading the spec, if you ever do get to that point, it's called Server Discovery and Monitoring. There's a link at the end. I would always have the PyMongo code alongside in your favorite editor because actually it makes it real to look at how this stuff implements it. And I've got to say, the PyMongo code is some of the easiest code to read I've ever come across. They put a lot of hard work and effort into making that a really manageable, easy to understand project. So I'll skip over this. Most of the people here seem to understand MongoDB, but this is just a standard set of Python calls that we might make. So we call Mongo client, we provide it with a host and a port. This is for a standalone instance, so we're connecting to localhost. We create a database and a collection, and then we insert, we find, we update, and we delete. And they're all JSON documents, but these are in fact, obviously DITs in PyMongo speak or in Python speak. So what happens when we're actually connecting to a replica set? So when I want to create a collection of replica set, I can give it some number of nodes. One node will work. In this instance, we're giving it 2 hosts, and we're giving it a name, replica set. So REPL set is the default name used by mtools, which I use to try out some of this stuff. mtools is a package provided by a MongoDB employee, which is just a great way of building clusters very fast and very easily. I do recommend you look at the mtools GitHub repository. So when we ask the client to do this, what happens? So the Mongo client actually returns immediately, right? So when you call Mongo client, if you called Mongo client in PyMongo 2, it would stall because it would be establishing connections to the server explicitly. Well, in the PyMongo 3 client, which I recommend everybody use if they're not using already, it returns immediately because it's actually spinning up some threads in the background. And those threads are monitoring threads that are designed to establish the topology of the cluster. So we've given it 2 hosts. So the way that the spec operates is we spin up in PyMongo 1 monitoring thread per server. Now we only know about 2 servers because we only told the Mongo client about 2 servers when we started, host 1 and host 2. So we start monitor thread 1 and monitor thread 2. And what these monitor threads do is they send a call that's called isMaster. Now, isMaster is an anachronistic name for a function. It should be called getStatus. It predates clusters and replica sets from when we only had a master-slave deployment model. But effectively, it's getStatus. And so isMaster will be sent to each one of these nodes. And the isMaster response that first returns, in this case, is to monitor thread 2. And it says 2 things. isMaster is false. That means I'm not a primary. And just to double sync that in, secondary true tells me it's explicitly a secondary, but it also returns a list of hosts. So remember, when a replica set is constructed, it knows about all the other members. So every member of the replica set is aware of all the other members of the replica set, and it continues to be aware by a heartbeat that this replica set handles. So monitor thread 2 gives you a bunch of data. Now, I ran this earlier on. It gives you actually quite a substantial dictionary of data, but the parts we're interested in for the purpose of this talk are it tells me the list of hosts. Now, in this case, I've run them all on the same box. I don't recommend you do that in production. And isMaster is false, secondary is true, and the REPL set name is REPL set. So what we do is we take the current topology, which right now is, I know about 2 nodes, the seed nodes that were passed into Mongo client, and I'm going to combine it with new information that I've grasped by running isMaster on the first node that replied. And that isMaster has told us that there's 3 nodes in this cluster, host 1, host 2, and host 3. Excuse me. So right now we've got a monitor 1 that hasn't returned, hasn't got a response from isMaster, a monitor thread 2 that has got a response, so we now know for sure that topology is telling us we have 1 real node in this cluster. And there's a setting, it would be set as RS secondary, there's a status field inside it, right? We also know that there's 3 particular hosts in this cluster, so we're going to spin up a 3rd monitoring thread. So now we have 3 threads, all monitoring the servers, all who have sent isMasters. We've had 1 isMaster reply. And remember, these threads are running in parallel, but they run with all of the constraints of the global interpreter lock and the threading issues with PyMongo. So they're not super lickety-split fast, right? So monitor thread is returned. Monitor 1 and 2 are still waiting for isMaster. In the meantime, what's your code doing, right? So your code start Mongo client, it returned immediately. So if it returns immediately, well, I'm going to do something with the database at some point. And so obviously I might call an insert, right? So I'm going to insert 1 field, simple document, AB, right? And it's the same replica set, so it knows it's an insertion to a replica set. This insert is going to block, right? And it's going to block because I can't write to a replica set unless I have a primary. Why? Because you can only write to primaries in a replica set. That's one of the constraints of the cluster. So the Mongo client will hold that right because it knows it doesn't have the complete state of the replica set at this point in time. It only knows about 1 secondary. So now I get an isMaster response from host 1, right? An isMaster response from host 1 tells me this is the primary node for this cluster. Right, now there's a server selection protocol. It's a whole separate spec. I'm not even going to talk about it today. That tells us how to pick servers to do particular operations. But the one thing that server selection knows is I can only write to a primary. So now that the primary's up, the client doesn't have to wait. It doesn't need to know about the rest of the cluster because the cluster will manage itself. The client knows if I can get a write to the primary will either satisfy the write concern and write to a majority of the nodes, or it will return an error to me, in which case I can return an error to the client. So I can go right ahead. So this write will succeed to the primary host, right? And in fact, the primary will respond with an OK, it will send a response back, and the insert will be satisfied. And in fact, you know, in most uptimes, this whole round trip will only take a matter of a couple of hundred milliseconds. So we have writes succeeding, we have a cluster topology that's got 3 monitor threads running, but we only know about 2 nodes. But at some point in time later, host 3 is going to respond, right? And at that point, we will update the topology again. We now have 3 monitoring nodes with 3 is-master responses, and we have a complete view of the topology, right? And this is what we call steady state. So this is the standard operating model for a cluster. And now what will happen is these threads will essentially wake up every 10 seconds and run an is-master, right? And the is-master will say, everything's A-OK. They'll update the topology and go back to sleep. And they may run in parallel. They may get slightly out of sync. That's all kosher, right? We don't mind about that because as long as we're running inserts that are succeeding, that will all be fine. Unfortunately, life has a nasty habit of intervening. The 6th saddest word in IT I've ever heard are, we have not experienced a failure, right? Or I have never experienced a failure. Guarantee. I remember I was one of the first people to use Amazon's S3 service in 2006. I was building an online backup system, and everybody who ever used it said, this stuff's never going to go down. And sure enough, for like 2.5 years, it didn't go down. And then it went down and took out the whole eastern seaboard of applications when the first region went down. Now, Amazon had told all the developers, you need to be multi-region to be fault-tolerant, resilient to the level that we want you to be. But everybody was piling their nodes into AWS. The default region was East Virginia. And they took out most of the startups in North America. And so, you know, we've never had a failure. That's just, you know, I guarantee you next week is going to be your first failure. And then you can never, ever say that again, ever, right? So life intervenes. So we whack the primary host, right? Now, the threads only wake up every 10 seconds. So you can whack the primary host, and the cluster could recover. And in a lightly loaded cluster, where there isn't many write activities happening, it might never notice. The topology would recover. The 10 seconds would come by, it would say there's a new primary, the topology would update, clients would never see it. But of course, in a heavily loaded cluster, and why the hell would you be using MongoDB if you didn't have a heavy write load? The whole point of NoSQL is to handle like thousands to millions to hundreds of millions of writes per second, right? Well, it's likely that before a monitor thread wakes up, the insert is going to hit the client. And the insert is going to hit the client, and now it's unpredictable what will happen in the client. It might send the request, but never receive a response. It might be halfway through sending the response, it might get a server close. We don't know, but all those errors will be wrapped up by the driver and sent back to the client as a connection failure exception. So you don't need to worry about sockets or timeouts or all of that crazy networking stuff. We do all that for you. All you need to know is, at the point when you were making a write, the write primary died in some way that interrupted your write. So what do you need to do in this situation? Well, you retry, right? And I'm going to talk about how many times you need to retry in a couple of minutes, but you're going to retry. So what happens when you retry? Well, the primary is down, and you retry the insert. Now, the Mongo client now knows the primary is down. It's no longer a surprise to it. So it's going to hold your write in the same way it held writes at the start. It's going to wait for that write It's going to put it in a queue, and it's going to essentially put out an all points bulletin. It's going to wake up all the threads. It's going to say, hey guys, hey girls, there's no primary in this cluster. That's a big deal. And it's going to essentially, instead of waiting every 10 seconds, it'll call those threads every half a second until a primary returns. Meanwhile, the insert is waiting, right? So elections, like I said, happen pretty quickly, between 2 to 3 seconds. So within a couple of seconds of putting out the all points bulletin and having all of these threads calling is master, we're going to elect a new primary, in this case, host 2. Now, host 2, it's probably, if you've followed our guidelines, it's the same topology or it's the same server size and scope and bandwidth and network and memory as host 1. So we shouldn't see a drop in performance. We're slightly less fault tolerant because now we're only replicating to 2 nodes rather than 3, but we've still got some replication. So now the insert will concede. Remember, the client will go, once I have a primary, I'm good to go. So now I can send the write straight into the server. And then the third node will recover. We'll send somebody down to the data center to plug that network cable in. We'll replace the power supply. We'll install a new node on a different AWS region. We'll put the fire out in the data center. We'll take the cup of coffee out of the network connector. And the system will recover. And now we're back in steady state. Note that in many cases, we may not have the same primary, and that's fine. The topology is comfortable with the primary moving around just in the same way that the replica set is. Now, you can change that. You can have a priority, which essentially tells you, I always want, if host 1 is available, to have it become the primary. What happens there is you're going to get a second election. So the minute that host 1 comes back, you'll have a new election. And every time you have an election, you're likely to get a retry error from your code or a connect failure. So we don't really want to promote lots of elections. So if you're managing a cluster, what typically we say is, if you're doing maintenance on a cluster, say you were upgrading all of the cluster members to a different version of the operating system, take out each secondary first, because secondaries will not interrupt the ability of the driver to write to the cluster, and then take out the primary last, and take it out at a time when your traffic is quietest. Now, we all know run services that are global in scope or that never turn off, but there's always a window when you have least amount of traffic, and that's the time to take your primary down. And the drivers will handle it, like I said, as long as you don't take the primary down for an hour. So what does this mean for you as programmers? Well, if you want to establish connectivity to a server, if you want to know I have connectivity to a particular server, calling Mongo client is meaningless. Mongo client will wait for 30 to 40 seconds before throwing an error because it's got those threads and they're waking up every 10 seconds and just saying, gee, I wonder if there's a server available. So getting a client object back doesn't give you any state information about the server. What you need to run is an isMaster yourself explicitly. So you can run client.admin.command. Admin is a database that's always available, so you don't need to create a new database by accident. And isMaster will return, and if it returns, then you've got a connection. If it throws an exception, then you know that you still don't have a server that's available. And isMaster has another couple of properties that are interesting. One, if you've got authenticated servers that require username and password, isMaster does not need authentication to run. It's purely, effectively a server ping. So you can very quickly run it on a server. It's also efficient. And of course, it gives you round-trip information to the driver, which the driver can use to establish what's the best server to use for a range of queries. So don't use Mongo client, use admin. What does it mean for queries? Well, find with recovery, remember what happens when we have a failure. It's going to fail, and then it's going to queue your query until it reestablishes connectivity with the cluster. So MongoDB is not a panacea. MongoDB will manage MongoDB, and MongoDB will stay up for as long as you want, right? Clusters are enormously stable, but we can't manage your network, your IT team, the rogue individual who walks into your data center and kinks a fiber channel cable, as it happened in Bank of Ireland a couple of years ago, or other external influences like I worked in Digital Equipment Corporation way back in the day. The number one thing that used to take out the whole data center, and this was a plant with 5,000 people, somebody with a JCB digging up the power cable. Happened all the time. So, those kind of outages, your driver is going to eventually time out and tell you things are wrong. So if the replica set doesn't return, then it means something else is up. So if you get a second connection failure, you need to percolate that up into your application, because that replica set isn't coming back anytime soon or in any meaningful time frame that makes a difference to you as a developer. So the guidance for drivers is, we're not going to automatically resolve your issues. You must participate in your own salvation, but you only need to retry once. So these retry loops you see in lots of code, which is for I equal 1 to 5 retry. Don't do that. One retry is enough. If it doesn't work once, it's never going to work, not in any time frame that matters to your program. So very important that you just do that one retry. What does it mean for inserts? Well, for inserts, we've got to be careful, because an insert might succeed, but the response might not come back. So we might send the BSON object and the command to insert to the server, the primary gets it, then we lose the network, and now the response doesn't come back. So we want to essentially establish that we don't do a double insert. And we do that by explicitly adding the object ID to the document before we do the insert. This is something the client would do anyway, but if there's already a document ID, it doesn't try and override it. Now, when we do the insert, either the insert will fail or will succeed and everything goes on as before, or it fails and we retry. And when we retry, if the insert had actually succeeded before, we'll get a duplicate key error. So remember, ID is a unique index on it. So you can't add objects with more than one same ID. So the duplicate key error will essentially identify that you've already done the insert. Now you're essentially back good as gold, and you can carry on as before. Now, updates are trickier, right? So updates change a document in place. So, well, I mean, there are 3 ways to think of this, and 2 of them I always think are a little bit odd, but people are odd, and they have different ways of programming. The first way is, it doesn't matter if I undercount, right? It doesn't matter if I undercount. So if I call update and it doesn't succeed, so what? Carry on. Maybe we're just counting log entries, and missing a couple isn't the end of the world, right? Or it doesn't matter if I overcount, in which case I can retry. I always retry every increment. But if you can't overcount or undercount, you need to think about creating an idempotent protocol for the database. And that's beyond the scope of the driver to help you with. You need to think about essentially turning updates into a series of writes, and those writes may be duplicated, and you can use the client to essentially eliminate duplicates, or more often than not, if you're using an event sourcing model, and I did a big talk on event sourcing, so maybe you can catch me again and catch that talk. If you're using an event sourcing model, if you turn all your updates into straight up writes, you can essentially eliminate duplicate writes by using the same kind of ID model to essentially add a unique ID to each write, and then look for unique IDs which are clashing. Or if you're using the ID field itself, it will send back a duplicate key error. And then you can accumulate and aggregate those values into the updates on the server side with our aggregation framework. But the whole point is, there are some operations that just can't be designed from a driver's perspective to be recoverable. And that's just the nature of a distributed, clustered database system. And it's one of the trade-offs that we make. You know, MySQL and Postgres and Oracle will tell you, we've never had a failure, right? Until you do have a failure. And when you have a failure, it's catastrophic. You can't write to the database at all, right? And what we're trying to do is avoid that catastrophic failure. 2 more kind of tuning fields for you. There are 2 parameters that you can put into the cluster. Connect timeout milliseconds is how long the monitoring thread will wait to establish a connection to a server when it's essentially pinging with his master. So this is something, again, we can't tell you. So if you're a high-frequency trader and you put a cage of servers in the New York Stock Exchange, right next to the New York Stock Exchange, well, connect time at milliseconds might be 2 milliseconds. If you can't recover a cluster in 2 milliseconds, you'll lose billions of dollars of transactions, right? On the other hand, if we ever put, I don't know whether we've got servers running MongoDB in the International Space Station, but you can be damn sure that the latency on a satellite link to that space station is going to be slightly lower bandwidth than between ourselves in a data center in Amazon. In that case, you might want to extend the connect time milliseconds from greater than 30 seconds. So the other one is server timeout milliseconds. So connect timeout milliseconds is on the thread. Server timeout milliseconds is on the client. And we used to use the same one, connect timeout milliseconds, but server timeout milliseconds is something we added because you essentially want to understand how long am I willing to wait in that queue to complete this write. And so if you've got a system that you can afford to queue writes up, if you've got back pressure, so imagine your writes are coming in off a queue that's a Kafka queue, and that back pressure can percolate down the Kafka queue even all the way back to the clients, then you can afford to set this timeout to be very high. If, on the other hand, you've got IoT events coming in that you need to process in real time, you want that to set much lower, in which case you'll get an error back to the client if you get that timeout. And so these, again, are areas where you can tune your environment to control what happens in your application. So all of this is documented in a great document written by an engineer in the US called Jesse Giroux Davis. He did a talk on this at MongoDB a year ago. So I'm kind of channeling his talk. He has a set of links. I don't know whether you can read that up here. I'll put all these decks up on SlideShare afterwards, so you should be able to get it if you go to my account name, Joe Drumgoole or J Drumgoole. The full monitoring and spec, server and discovery monitoring spec, is on GitHub. Very easy to read and download, and we accept change requests on that. If there's something you don't understand, do come and ask us. But the key thing is, this has established a consistent model for how drivers interoperate with clusters, both sharded and replica sets, although I only talked about replica sets today, for all drivers. So all drivers in MongoDB now comply with this spec. So now, if you're writing code that more or less works in PyMongo, that same code pattern should work in Ruby and Java in the same way. It may work slightly differently in C because the semantics for single-threaded drivers are different from multi-threaded drivers, and we typically don't build multi-threaded clients for languages that don't have explicit threading baked into the language. Otherwise, we'd be pulling too many third-party libraries in. And so the cluster will manage itself, but the driver requires your help. So when you're writing MongoDB client code, don't forget that you're in a distributed network system. You know, the 7 fallacies of building distributed systems is as old as the hills, but it's still true. And so what we do is try and help you as much as possible, but you must participate in your own salvation. So you must engage and read this spec. You're not going to become an expert from listening to my talk, but reading the spec will really help you to understand how topology is managed inside a driver cluster. That's pretty much it from me. Those of you who read the talk summation will have gone, what about inserts and queries and updates? How do they work? Well, when I started to do this talk, I hadn't really got my head inside the driver spec. I used to run pre-sales from MongoDB, but they wouldn't let me write code in pre-sales, so I moved to developer advocacy because now I can write code at least half the time, and then I have to talk about writing code the other half. So all the operations in MongoDB on the client side, apart from topology management, which is the most complicated and interesting part, run the same model. Validate the parameters, and there's lots of parameter validation. Convert the data into BSON. Now, BSON, actually, there's an intermediate format called SON, which is essentially an ordered dictionary. So SON objects have the property of being able to convert themselves to and from BSON. We take the SON object, and then essentially we look for a socket in the socket pool, and within that socket or that server, we ask for a server that's suitable for this operation. This is the server selection protocol I talked about. Again, there's another big spec also in GitHub, which I can't go into today. So the most simple server selection is I need a primary to do writes, but for reads I can use secondaries. Once I've found a server that fits the selection, I take the BSON object, I inject it down the server socket. It's just a straightforward TCP/IP socket. I wait for a response object, which comes back in BSON. I unbundle that into a SON object, and then I unwrap that into essentially dicts or arrays or whatever the client expects to see. The only subtlety with queries is we don't actually return anything. When you do a query, we just return a cursor, which is client-side only. And when we query a cursor, it's only when you ask for a cursor element that the iterator goes and gets a list of elements. And when we query a cursor, we get 100 elements at a time. So that's the MongoDB client, PyMongo client. I've got time for some questions if people want to ask questions. Otherwise, thank you very much for listening today. Question, down the back there. Wait for the mic, otherwise I'll have to repeat it. I'm so lazy.
Okay, the first question is that you mentioned that people often use BSON serializing logic themselves without using Mongo client actually. So maybe it would be a good idea to just refactor module for serialization and deserialization outside the Mongo client, because if I remember correctly, I wanted to use serialization logic. Yeah, just BSON. Yeah. And I had to install a whole Mongo client package, and other colleagues came to me asking about why do we need Mongo here, because I just wanted to use BSON.
Yes, you make a good point, but we also, it's a trade-off. We're here to support MongoDB developers primarily, and for them, it's easier if they just pull one package, which is a totality of what they need. If we were to separate that package out, then it makes their lives more difficult. So it's a trade-off. You have some pain because you just want to use BSON, but the PyMongo developers have a much easier life because it's all bundled in together.
Yeah, I see. Could you also revert to the slide with logic for retry of insertion to database? Yeah. So this logic, you insert first, then let's assume it fails. Yeah. Yeah. Then you insert again, yeah. But you said this can throw duplicate key error, yeah? But you won't catch this error because the second insert isn't in try block, it is in accept block. So the second accept won't catch it, if I'm right.
My error. I will amend that code.
Okay, so thanks.
Yeah, Anna also works for MongoDB. She's allowed to make announcements.
I just wanted to say really quickly, if any of you use MongoDB with Scientific Python or NumPy, you should come talk to me because we're developing a new package and I would love to get some feedback.
One more question here.
Thank you for the conference. I would like to know about the motor driver. What's the plan for porting it to PyMongo 3?
Say again?
About the motor driver, the motor async heal driver.
Never heard about it. I'd have to ask the driver team.
Okay.
come to me afterwards. If you give me the question, I will send an email to the driver team and find out what their plans are.
Okay.
Okay.
Thank you.
Do you know about libraries like Mongo Engine, and what do you think about this? I mean, it makes it look like it's a normal SQL database and makes it look like all the same.
I have a personal opinion. This is not a MongoDB opinion, and all developer opinions are personal opinions, no matter what people say. Why would you? Why would you use something that makes MongoDB look like an SQL engine? The whole purpose of using MongoDB is to make the things you put in the database very similar to the things you interact with in your programming language. Why would you obfuscate that layer with an SQL layer? I know what you're going to say, which is I already have SQL code that I want to write to alongside, right? And if you have a compelling reason that you need to write SQL queries or write to the database, then absolutely use a layer. Now, one of the things that we have in the commercial offering is a BI connector. It won't allow you to write to MongoDB, but you can definitely do SQL queries to MongoDB. So we support the idea of querying MongoDB using SQL, and there's a range of, there's a mapping capability that essentially allows you to unwrap arrays and nested objects into new tables so that you get a tabular view of your nested data. But you can't write. You've got to write with a driver. So Mongo Engine may allow you to write, in which case, yeah. If you absolutely have to use SQL, then, I mean, use the tools you need to use. I mean, the great thing about Mongo Engine is I bet you underneath the covers is using the PyMongo driver.
Just to complete about Mongo Engine, it could be useful to validate document before MongoDB 3.
So, didn't talk about it today, but we have document validation.
Yeah,
right?
Since MongoDB 3 point, yeah.
Yes.
Before there are no validation document, so Mongo Engine could easily validate your document.
Well, so I was at a conference recently, and somebody quoted an engineer from their organization. I think it was Gilt, and he said, he formed a law called Andre's Law, which is we can build it today, or we could wait 6 months and Amazon will build it for us. Well, there's a little bit of that in MongoDB. Things that you build today, we're probably going to build tomorrow. So if there's a broad community of people who need a capability, we spend a lot of time talking to the community. So I can't make any future looking statements on what we will or won't do, but surprise, surprise, having some kind of SQL capability against the database has been something that's been talked about for a long time, and we introduced that in the last release of MongoDB 3.2. We're going to continue to enhance that capability. So we rarely drop features. This is why isMaster still runs, right? isMaster was the original status call from the very original version of MongoDB. So one of the good things and one of the testaments to our CTO is he's obsessive about backwards compatibility. So we tend not to break stuff in the past in order to bring stuff forward. So lots of our customers are still running on MongoDB 2.2. Shame on them, but they are. One down the back there.
Yeah, I have a question about automatically recover of the cluster. You told us that when you have cluster of 3 nodes and primary fails, then afterwards new primary is available. And I had a situation not far ago that I have a cluster, a five nodes cluster, and when 3 of the nodes failed, and one of them was primary, then I ended up with 2 secondaries who couldn't elect new primary, and this could be fixed only by either forced reconfiguration of the cluster by Mongo, or by waiting to at least one of the failed nodes recovers. Is this normal behavior, or?
That is normal documented behavior. That's the way the cluster is meant to respond. So a cluster will only recover a primary if a majority of the nodes survive a failure. And those majority of the nodes are connectable, which is to say they're all in the same side of, say, a network partition. So if you lose a majority of the nodes, the two nodes that are left will come up, but they'll come up in secondary mode only. So the driver will say, well, I can't write, but that select server spec says I can still query. So I can still write queries to the secondary nodes, but any write will fail. And that's what I mean about the catastrophic failure. A catastrophic failure is where I can't elect a primary because I don't have a majority of the nodes. Now that catastrophic failure can be caused by failure to isolate your nodes or through a data center failure. It doesn't really matter. I mean, one of the things that I say is MongoDB nor any other distributed database is not a panacea, right? People ask for 99.999999 uptime because they don't know what that means, right? And then I say to them, do you know that your power provider for your national grid doesn't have that level of uptime? So what are you going to do when the national grid goes down? And they say something dumb like, but we have a generator. And I say, who's it for? Nobody has a network. The whole grid is down. Yes, you're running, but the rest of the world can't connect to you. So it's just, you know, we're responsible for ourselves. The rest of the world has to worry about the rest of the world. So we'll make sure the cluster recovers. If you set it up so that the nodes are independent of the single points of failure within your domain of control, then you shouldn't have 3 nodes failing at the same time. If that happens, then that means 2 things have happened. You've joined them to a single point of failure, like a single node or an Amazon region, or more often than not, you poisoned your own cluster. So you might have destroyed your cluster with a code error. So that happens all the time.
Okay, thanks.
Okay.
No more questions?
Go forth and write excellent driver code.
Thank you very much.
And the pretty view is able to